lost 25% of the value of that investment. I made the wrong choice. I did not do Bayes' rule correctly. Okay. As a result of which, I went back to work sooner than I intended. Okay. Suppose the proportion of, among mutual fund managers, the base rates of high, medium, and low ability mutual fund managers is probability high 0.25, medium 0.5, and low 0.25. Okay? So kind of a bell-shaped distribution of ability. And by ability, I mean ability to pick stocks well, not ability to bamboozle the client, which may be the more relevant dimension of ability, but we're not going to address that. It turns out, if you're choosing between an index fund and an actively managed mutual fund like this, unambiguously, in all cases, the right way to not lose money is to put your money in an index fund because basically there aren't any high ability mutual fund managers. Over time, they all lose value relative to the market. So that's just a piece of information for you going forward. Suppose that the probabilities of each type of manager having one good quarter, meaning that they beat the market, are the probability of having a good quarter if you're a high type is 0.75, probability of a good quarter if you're medium type 0.5, probability of a good quarter if you're low type 0.25. Okay? So you could be a crappy manager and sometimes get lucky, is what this is saying. Or you could be a really good manager and sometimes get unlucky. If we see a manager having a good quarter, what is the probability that they're high ability, right? So what's the hypothesis? Hypothesis is the fund manager is good, of high quality, high ability. What's the signal? 1 quarter of positive of beating the market. Positive above normal returns, I think is what that's called. Okay. Here's how I want to use this box. So this box is going to have an area of 1 again. And this time it actually is going to have dimensions where one dimension is going to be what type of manager you are, and the other dimension is going to be how likely you are to have a good quarter. Okay, so let's just chop this box up into 3 chunks vertically. Okay, and so this box contains all the high ability managers, and this one contains all of the medium, and this one all of the low. Now it doesn't really contain them. What it does is it contains the probability that any randomly selected manager is 1. Okay, I'll just make that look a little bit more like half. Okay, so that gets me my base rates. Right? The probability that a randomly selected manager's high ability is 0.25. Probability that their medium is 0.5. Probability that their low is 0.25. Those are my base rates. Now, let me stick in my conditional probabilities that I've already been given. We don't have the conditional probabilities for how likely the signal is given the true state of the world, then we can't make progress. But let's just roll with the idea that we've been told that the probability of seeing a good quarter conditional on a high ability type is 0.75. Yeah? And then the probability of having a good quarter if you're a low ability type is equal to 0.25. And this is I'm a little bit unhappy with this, but let me just sort of plug that in over here somewhere where I can fit it. This is the probability of having, get to fit. Probability of having a good quarter, given that you're, medium ability type, is equal to 0.5. Okay? Now, what I've done is that I've carved out these areas, because this is a 1-by-1 box, the areas of those different boxes are joint probabilities, right? So, it is only out of a deep, deep sense of respect for Alain de Chambry that I do not require him to erase his boards. I'm imposing on myself a lower status, which I think is professionally appropriate. Okay. So what does Bayes' rule tell us about the conditional probability we're looking for? Bayes' rule, Bayes says that the probability, can everybody see this underneath the screen in the back? The probability that you're a high ability manager, given that you've given that you've beaten the market for 1 quarter, is equal to the probability that you're a high ability type and you post above normal returns for 1 quarter, divided by the unconditional probability of any randomly selected manager posting good returns. Okay? All right, now we go over here. And let's build up what these parts are. So that's a joint probability. That's what the comma means. The probability that you're a high ability type and you post good returns is a joint probability. Okay, so the joint probability that you're a high ability manager and you post good returns is equal to, we already know this, it's the probability that you're a high ability manager times the probability that you post good returns, given that you're a high ability manager. And what's that? That's this thing. I'm going to call it A. Okay? Oops. And it happens to be equal to 0.1875. Okay? So if you just randomly selected a manager on any given quarter and said, what's your ability type, and did you post good returns, there's a 0.1875 chance that they'd say I'm a high type and I posted a positive return, or an above market return. Now, what's the unconditional probability that a randomly selected manager, before you ask them their type, would say that they had a good quarter? Okay? Well, it's just a sum of joint probabilities. It's the probability that you have a good quarter, that you're a low type and have a good quarter, plus the probability that you're a medium type and have a good quarter, plus the probability that you're a high type and have a good quarter. So it's just a bunch of of joint probabilities. And so I'm going to skip this step where I write out the product of what those joint probabilities are, because by this stage it should be painfully apparent what they are. That's the joint probability that a randomly selected manager is of medium ability and has a good quarter, and that's the probability that they are low type and have a good quarter. Okay? So it's just equal to C, I did this in the wrong order, C plus B plus A. Yeah? And that happens to be 0.0625 plus 0.25 plus 0.1875, which is equal to 0.5. Okay? So given the base rates and the conditional probabilities that I specified, the unconditional chance of any randomly selected fund manager having a good quarter is half. Okay? So if half the time you're going to see good, and 0.1875 of the time you're going to see good and high, you're basically just renormalizing this probability by the likelihood that you would have seen good in the first place. That's what Bayes' rule is doing. Okay? So this thing here, it's just that joint probability, which is A, divided by this unconditional probability, which is the sum of joint probabilities. Okay? And that is equal to, in this case, 0.1875 divided by 0.5, which is equal to 0.3750. Okay? That's Bayes' rule in action. Now, one of the things we're going to see before long is that lots and lots and lots of people, by which I mean everyone, basically, well, no, not everyone, but lots and lots and lots of people, think in a situation like this that the probability, if you see a good signal, the probability that the fund manager is of high ability is bigger than that. Okay? Overwhelmingly, the error that people make in cases like this is that they systematically think it's way, way more likely that the fund manager is good if they had good returns. They over-infer from limited information. And similarly with the HIV test, overwhelmingly, people, even quite highly educated people, and I think it's the case in some cases. Oh, no, that's a little bit. I'm sorry, I was about to say something much more damning than the truth. But overwhelmingly, lots and lots of ordinary people think that if you've got a test that is 99% accurate for HIV positive status, and you got a positive result, you are damn near 99% likely to have HIV. Lots and lots of people think that. Okay. So what I want to do is I need to bail out of here. Is everybody done with what's on the screen tonight? I want to open up a few slides from my notes from last year. So these are going to look a little bit odd because I didn't get a chance to modify them. So this whole title you can just ignore. We're going to come back around to what base rate neglect is. But basically, last semester, I did something that I decided not to do this semester, which is I gave at the beginning of the semester, I gave students a survey asking them a bunch of tricky questions. And this is a survey that the other instructor for this class, Botan Kosetti, has been administering to his students for many years, and he's compiled really nice Excel spreadsheets, and he has these really nice graphs of exactly the degree and type of irrationality of UC Berkeley students over the years. And basically, this question on the survey just asks you the exact scenario of the HIV test and asks exactly the question that we figured out earlier: what's the probability of HIV positive if you get a positive test result? This is the data from my students last year. The modal answer was 99%. Most of the people, the largest number of people in the class said 99%. 72% were above 90%. Okay, and only 10% gave the correct answer. That's UC Berkeley students. Now, this is not supposed to be an insult. I get this stuff wrong as well, and I have a relatively remunerative and reasonably high status job. So it's not like you can't make your way through the world without being able to do Bayes' rule. And this is just the math that we've just been through. But it's just a fact. This is what we do. Even when we are, right? So this kind of comes back to Palace's earlier question. In some sense, it kind of almost doesn't matter whether what we're technically assuming is that people do the math or whether what we're technically assuming is that they act like they can do the math. They can't do the math. Not only they can't, it doesn't occur to them to do the math right. You're supposed to have at least Math 16B under your belt by the time you take this class. It doesn't even occur to people to do the math right. It's extremely unlikely that they are behaving as if they can do the math right when they can't when asked to. It's just, I take the point about the billiard player. If we ask the billiard player what are the laws of physics, they wouldn't know. But if we ask the billiard player, what set of thought processes are you going through to figure out what shot to make, they would be able to tell you, I believe, something fairly systematic, even if it had nothing to do with the laws of physics. And the fact of the matter is that when you're actually asked, and it's important for a decision, to figure out the outcome of your choices, to calculate an inferred probability, there is only one right way to do it, and you actually have to use math. So in some sense, it's a bit of a moot point whether our assumptions that people do the math or act like they do the math. They fail on both counts. Okay. Here's another example that's going to be not quite so immediately obvious, although it's a lot of fun. And next, on Thursday, we'll poke into how we might model this error. This is a real favorite. This is from the required reading for this section, Heuristics and Biases, by Tversky and Kahneman. It's really important to note that this paper is, oh no, is this one also Kahneman and Tversky? So these guys made a deal earlier in their career that they would just, every other publication, they would switch the order of their names. So what's Kahneman and Tversky and what's Tversky and Kahneman tells you only where they were in the sequence of publications. All right, so consider the following question, and you'll see this in the reading. Linda is a 31 years old, I'm not sure why there's an S there, is a 31-year-old, single, outspoken, and very bright. Oh, I see, she is 31 years old, single, outspoken, and very bright. She majored in philosophy. Okay, these are all signals. As a student, she was deeply concerned with issues of discrimination and social justice, although we don't know exactly what issues, and she also participated in anti-nuclear demonstrations. This paper was written in 1974. Okay, so we have a bunch of signals about Linda. And the question asks you to make inferences about the state of the world, a hypothesis, okay? Please rank the following statements from most to least probable, 1 to 8. And then what you have here in parentheses is the average ranking of their subjects, okay? So hypothesis 1, Linda's a teacher in elementary school. Hypothesis 2, Linda works in a bookstore and takes yoga classes, et cetera, et cetera. Linda's active in the feminist movement. Linda's a psychiatric social worker. Linda's a member of the League of Women Voters. She's a bank teller. She's an insurance salesperson. She's a bank teller and is active in the feminist movement. And the ones that they really focus on are the probability that Linda's a bank teller and the probability that she's a bank teller and is active in the feminist movement. And people, on average, think that it is more likely that she is a bank teller and a feminist than that she is a bank teller in the first place. Okay? That's not just bad math. That is manifestly not possible. Right? At best, the probability that she's a feminist bank teller might be the same as the probability that she's a bank teller if all bank tellers are feminists. But it is not possible for there to be more feminist bank tellers on the planet than there are bank tellers. You don't have to know whether or not people are computing Bayes' rule to say this is a mistake. Okay? And it's not like when we say that people have non-standard preferences. Okay, fine, your preferences are your preferences. And if people have non-standard beliefs, well, I believe that the world is flat. Okay, all right, that's kind of not such a good example. But I believe that the moon landing was staged. You guys, have you heard this one? There's a lot of people out there who think that the moon, all of the moon landings, were actually shot on a soundstage somewhere in Hollywood, right? Including the Russian ones. I'm not sure how that fits in. You're free to believe whatever you want if we don't actually have any information. But it's not up to you to decide what the laws of reality are. You just don't get to make statements like this and have us not be able to say it's a mistake. It's a mistake. Okay? Okay, so this is called the conjunction fallacy. And this is the thing I really like. This is in the paper. Subjects ranging from those with no education in probability and statistics to those with multiple graduate courses under their belt all commit this mistake in large proportions. Okay? So in some sense, maybe it's important to distinguish between people can't do the math, which then kind of makes you feel bad, and people don't do the math, or they don't think in terms of the math that they should be doing. Manifestly, if you have real stakes on the line on getting this answer right, there is one right way to do it, which is to consult the mathematical reality of the situation. So the fact that people don't, it may not reflect the fact that they can't. It may just mean, who knows what it means, right? But it's going to be kind of, I think, a little bit irrelevant to distinguish between they act as if they don't know the math and they don't know the math. Was there anything else I wanted to say? Okay, so you can read this in the paper. I don't want to focus on this now. There's this thing that Kahneman and Tversky call representativeness heuristic, which is all of the signals that we got, right? She goes to these protests, she studied philosophy, she's, they all sort of signal that she's a liberal. And that she's, and back in the 70s, these signals would have been taken as very strong signals, okay? This was in the time of the Equal Rights Amendment, and it was a big deal. And so what people do, Kahneman and Tversky postulate, they're psychologists, mind you, not economists, is that they say people form a picture in their mind of who Linda is based on the signal, and feminist bank teller fits that picture better, right? Their image of a feminist bank teller fits their image of Linda better than their image of a bank teller, okay? And so they just say, well, yeah, that's more likely, which is completely different than doing the math. And it is exactly the same as not doing the math. And what I hope to show you is we're going to try to come up, as we always do over and over again in this class, we're going to come up with a mathematical model that preserves as much as possible of Bayes' rule, but tweaks it in a way that can potentially explain this mathematically. Okay, see you on Thursday.